Hey everyone, and welcome to the Explainer. Today, I want you to think of yourself as a bit of a pattern detective. We are about to crack the code of mathematical sequences using some incredibly elegant foundational principles. If you've ever looked at a string of numbers and wondered, what hidden rule actually connects them all, well, you're in exactly the right place. So grab your magnifying glass because we are going to make this whole thing completely transparent.
Here's our energetic mission briefing for today. We've got 6 specific steps to decode these sequences. First, sequences and terms defined. Second, additive versus multiplicative change. Third, recursive and explicit rules. Fourth, working the tables. Fifth, misconceptions and edge cases. And finally, number 6, our recap and transfer task. Let's get right into it.
Section 1. Sequences and terms defined. Let's get familiar with the basic vocabulary for our investigation.
Okay, let's dive into this. A sequence is, at its core, a lineup of suspects. It's an ordered list of numbers forming a distinct pattern. In formal mathematical language, its domain, which is just the set of inputs or positions, is a subset of integers. You can kind of think of it like a strict numbered row of chairs. Now, each individual suspect sitting in a specific chair in that order, that is called a term. So when we talk about a sequence, we're looking at the whole entire lineup. But when we say term, we're pointing at one specific individual in that lineup.
Section 2. Additive versus multiplicative change. Now that we know who we're interrogating, let's look at the 2 distinct ways these sequences can actually grow or shrink.
So right here, we're comparing our 2 prime suspects of change. On the left, we've got constant additive change. We also call this a common difference. This represents an arithmetic sequence which grows by adding or subtracting the exact same value every single time. It creates a very steady, linear progression. Now, on the right, we have constant multiplicative change. This is known as a common ratio, and it's basically the engine behind geometric sequences. Instead of adding, the sequence grows by multiplying by the exact same factor each time, which leads to explosive exponential growth. One steps steadily while the other leaps.
Section 3, recursive and explicit rules. Let's see how these changes build into the actual rules we use to write these sequences algebraically. Notice how we contrast our 2 main tools for cracking the sequence here. The recursive rule is literally like a step-by-step walking guide. It tells you exactly how to find the very next term, but to do so, you absolutely must know the previous term. For instance, to find the 5th term, you need the 4th. But then, we have the explicit rule. Think of this as your teleportation master key. It allows you to jump directly to any specific step in the sequence without needing to know any of the previous ones. If you want the 100 term, you just plug the number 100 into the formula, and boom, you're instantly there.
Section 4. Work in the tables. It is time to take these rules out of the textbook and right into the interrogation room by looking at some actual data.
This brilliantly illustrates our first suspect, an arithmetic sequence. Look closely at the table. On the left, we have the index, denoted as n, which is just its position in line. On the right, we have the term value. As our index moves from 1 to 2 to 3, what happens to the output? It goes from 5 to 8 to 11. We are seeing a constant additive change of plus 3, because we're adding exactly 3 every single time. We know beyond a shadow of a doubt that this is an arithmetic sequence.
Now contrast that previous table with this one. Notice how much faster the numbers get larger. Our inputs are still 1, 2, 3, 4, 5. But our outputs leap from 2 to 6, then to 18, 54, and suddenly 162. We aren't adding a constant number here. Instead, we're dealing with a geometric sequence, driven by a constant multiplicative change. Every single term is multiplied by 3 to get the next one. That is our common ratio.
So how do we actually calculate a missing number if I asked you for, say, the 20th term of a sequence? Well, here are our concrete detective steps. First, identify the requested index. Remember, the index, denoted by n, is just the address or the position of the term in the sequence. Second, look at the first few terms and determine if the pattern relies on a common difference, meaning it's arithmetic, or a common ratio, meaning it's geometric. Third, once you know what kind of sequence you have, you just plug that index n directly into your explicit rule to calculate the exact value of that specific term. Absolutely no need to walk through all 19 previous steps.
Let's pause our investigation for a quick second and put your skills to the test. Take a look at this sequence. 10, 7, 4, 1, and so on. I'll give you a second. Is this an arithmetic or a geometric sequence?
If you guessed arithmetic, you are absolutely right.
Now, some people get tripped up here because the numbers are decreasing, but the reasoning is that even though the values are going down, it still possesses a constant additive change. In this case, we're adding a -3, or simply subtracting 3 repeatedly. A common difference can definitely be negative.
Okay, let's pose our second check to see if you can crack the code on a rapidly growing list of numbers. Look at 2, 10, 50, 250. What do you think, arithmetic or geometric?
The answer is a geometric sequence, and the proof lies in the constant multiplicative change. To get from 2 to 10, we multiply by 5. From 10 to 50, we multiply by 5 again. Because each term possesses that exact same common ratio of 5, it strictly follows the rules of a geometric sequence.
Section 5, Misconceptions and Edge Cases. Let's move on to a critical plot twist where we address some common mathematical traps that catch a whole lot of people off guard.
There's this really persistent misconception out there. Some people loudly claim any increasing sequence is geometric. Well, assuming every sequence that goes up is geometric is kind of like assuming every tall person plays basketball. It's just not true. As we saw earlier, an arithmetic sequence with a positive difference also increases. Just because a pattern goes up doesn't automatically mean it's multiplying. Always check the differences between the numbers before jumping to conclusions. And here is a very important edge case warning for your notebook. If you spot a sequence with a common ratio of 0, meaning every term after the first is just 0, or if you spot a fluctuating pattern where the ratio changes from step to step, you have to be super careful. These scenarios break the strict standard rules of a geometric progression. A true geometric sequence must have a constant, non-zero multiplicative change across the entire board.
Section 6, Recap and Transfer Task. The crucial point is coming up right now as we debrief and put your newly sharpened skills to the ultimate test.
Let's lock in everything we've learned today with 3 key takeaways. Number 1, an arithmetic sequence grows by a common difference, while a geometric sequence grows by a common ratio. Number 2, recursive rules tell you how to find the next term from the previous, but explicit rules use the index to find any term directly. And number 3, always check for a constant rate of change across the entire table to avoid being tricked by edge cases or misconceptions.
We're going to end today's explainer with a provocative real-world scenario. Imagine a scientist is tracking a bacteria population in a lab, and this population perfectly doubles every single hour. Based on everything we've discussed today, is that biological population growth modeling an arithmetic or a geometric sequence? Think about what doubling really means mathematically. I'll leave you to confidently apply your new knowledge about multiplicative change to figure that one out. Thanks for being a great pattern detective with me today, and keep exploring.